So we're just doing the power functions today. Radical functions will be on Monday. You guys are going to be able to graph and analyze power functions. And power functions, they are functions that are in the form of f of x equals an to the x, ax to the n power, where n is a non-zero constant number. So power functions are things like 3x squared or negative 1/5 x to the third, okay? Or even 2x to the negative a power. Even that is an example of a power function. Same thing with like negative 4x to the 1/2. That too is also a power function because it's in the form of a, some number, x, then raised to some non-zero constant number. Now, do realize that if n is even, if your exponent is even, and a is positive, your coefficient is positive, then it's going to look somewhat like this first picture, where both ends of the graph are going to go up on your graph. However, if n is even and a is negative, then it's going to look some variation like the graph on the right, where both ends point down. Okay? Think about this one that I wrote, this very first one. This is a quadratic, 3x squared. Your a is positive and your exponent is even, so it's going to look somewhat like this. But that also applies to anything raised to the 4th power or the 6th power or the 8th power. Both ends are going to be up if a is positive. Both ends are going to be down if a is negative. However, if n is odd, your exponent is odd, and a is positive, then it's going to look like so, where the right side is going to go up and the left side is going to go down. But if n is odd and a is negative, it's going to be the opposite. The left side is going to be pointing up and the right side is going to be pointing down. So like in example 2, where I have a negative 1/5 x to the third, the exponent is odd, so it's going to be one of these two. And since a is negative, it's going to look more like that graph. Okay? So you got to look at the coefficient and you got to look at the power. Power is another word for exponent, another word for degree. Okay? Another word for degree. So let's analyze and graph this function 1/2 x to the 4th. We're going to find all these features of this particular function, and we're also going to graph it. Okay? But let's start with graphing first. As you know, we can always make a table to graph these functions, right? We'll pick some values for x, plug them in, and we'll pick some to get our values of y. Let's see, negative 2 to the 4th power is 16. What's half of 16? 8. So negative 2, 8. That doesn't fit. I'm not going to worry about it. I'm going to keep going. Negative 1 to the 4th power is positive 1. 1 times 1/2 becomes 1/2. That one I can graph. And probably just for the sake of it, I am going to put that point somewhere up there so I know it's going like that. When I plug in 0, 0 to any power times any number is going to be 0. So I got 0, 0. When I plug in 1, I get 1/2. And when I plug in 2, I get 8. Which makes sense. A is positive, n is even. So both ends should point up. And I just connect. I do my best job to try to connect these points. Oh, Lord have mercy. There we go. Now taking a look at this, we can use our knowledge of all these things we talked about at some point in time in this year to determine this. I'll take a volunteer in the classroom. Simon, what's my domain?
Negative infinity to positive.
Negative infinity to positive infinity. Okay, how about this? Classroom, online. Classroom, we'll do this one together. Online, classroom, online. Okay, yes. Online, what's the range of this function? Take a volunteer.
Bracket.
0 to 100. Oh, bracket 0.
Bracket,
0, comma, infinity, parenthesis.
good stuff, yes. The 0 is included. That's the lowest it goes to the highest that it goes. Wonderful. Intercepts. We are talking about x-intercepts and y-intercepts. In other words, where the graph crosses the x-axis, the y-axis. Colton.
Both of them would be 0, 0.
Yes, 0, 0. If it hits at the origin, it's an x-intercept and it's a y-intercept. Okay? Now in behavior, this is new. In behavior is exactly what you think it is. It's the behavior of the ends. What is happening at the ends of the graph? So that means over here on the negative axis and over here on the positive x-axis. And how in behavior is written, because I write big, so I need the space, it is written in limit notation. Y'all remember when we did limits at the beginning of this unit? Okay, so in behavior is written in limit notation. It's the limit as x approaches negative infinity of your function. That is talking about the left side of your graph. So as x gets closer to negative infinity, that means I can start in the middle, and as x is getting closer to negative infinity, what's happening to your y's? To what number? To infinity. So on the left side of your graph, as x is approaching negative infinity, your y's are approaching positive infinity. And that's exactly how you would write. Remember before when we were doing a continuity in 3-1, it was approaching a particular number. Well, now within behavior, we're talking about, is it approaching positive infinity, negative infinity, could be approaching a number. It really kind of just depends on the power function. That's the left side. We have to do the right side as well. As x approaches positive infinity, that means we're talking about on the right side. So again, as x is getting closer to positive infinity, what's happening to your y's? They're increasing. They're going to infinity as well. So this is going to equal infinity also. No, they will not always be the same value. It really depends on your power function. But that would be your end behavior. Any questions on end behavior? Continuity. That's back in 3-1. Continuity, that's your, is it continuous, essentially? Is it a continuous function, or do we have some types of discontinuities? Online, what say you?
It
Continuous.
is continuous.
It is continuous. So then you just write that. It's continuous. There are no holes, no jumps, and no infinite discontinuities. But it is increasing. Classroom from where to where? Sit. It's increasing from 0 to infinity. What do I need around 0 and infinity? Close. It's parentheses. Because remember, it's not an increasing nor decreasing there, so we can't define it. Only on endpoints. Only on endpoints. Where's the decreasing, someone online?
Negative infinity to 0.
Negative infinity to 0. Very good. And there you go. We graph and analyze this power function. Wonderful job. Great job. Very good. Let's look at the next one. All right, let's look at this one. We are going to graph and analyze negative x to the 5th. A is negative and n is odd. So you should have an idea of what it should look like, correct, based off of your drawing? All right, well, let's make a table. And do realize that that 5 is only applying to the x, not negative x. So I'm going to use my same values again. And I'll help you guys out on this part. I'll do the graph part, then you guys give me all the information on the side. So when I plug in -2, that is saying negative -2 to the 5th power. Well, -2 to the 5th power is a -32. But then there's a negative on the outside. So it makes it positive. I'm definitely not graphing that. That's too far. A negative -1 to the 5th power becomes a positive 1. Of course, 0 to any power is still going to be 0. When I do this next x value, what's that going to equal?
-1.
-1. And then this one here is going to equal a -32. So that is why those power functions where a is negative and n is odd, they point up to the left and point down to the right. Okay? Someone online, give me the domain.
Negative infinity.
I think I heard you right. Oh, that's why I can't hear you. I had it in my computer, not my board. Okay? Should be able to hear everybody now. Someone different in the classroom, give me my range. This one is a -infinity to +infinity. It goes all the way down to -infinity, all the way up to +infinity. Wonderful, wonderful. Online, let me hear from somebody different. What are my intercepts?
X and Y intercept would be 0, 0.
Yes, 0, 0 for my X and my Y intercept. Wonderful. In behavior classroom, I'll help you out with the limit notation. The limit as x approaches -infinity of your function. So again, as x is going towards -infinity, what is happening to the y's? It's going to +infinity. So again, as you go this way, as the x's are getting -5, -10, -20, the y's are continuing to get positive and they're continuing to get bigger. So then the limit as x approaches +infinity of your function, -infinity. Very good. Because again, as we go this way, as your x's get bigger, your y's are getting bigger to -infinity. Beautiful. Online. Continuity?
Continuous.
That it is. No holes, no breaks, none of that. Classroom. Continue us. -infinity to, ooh, careful, careful. We use 0 as that point for in behavior, because as we go to -infinity to +infinity, but increasing, decreasing, we always read from left to right. There's none. Okay? It's not increasing at all. Because if I read from left to right, online, it's actually going to be decreasing. From what to what? Negative. Good job. Questions on these? Pretty straightforward.
Can you show the slide with the pictures again?
Sure can. And then I heard somebody say something else.
Yeah, I don't necessarily get the intercept part.
Okay. So the intercepts, we're talking about where does the graph cross either the x-axis or the y-axis. And so when we look at our graph, we can see that that point where it crosses the x-axis and y-axis is actually the same for both of these functions. And so we just need to identify what it is. So since it crosses at the origin, our intercepts, x and y, are the same. It's 0, 0. Same thing with this function. It crossed the x and y intercept at the same point, so it is 2 is 0, 0. So pretty much we're just looking for the point or points where it crosses either one of those axes.
Okay, thank you.
You're welcome. And then here's the picture of the graphs one more time before we move forward. So if you were curious about this negative one, we're going to talk about that in right now. The fractional ones, that's a part of radicals, and we'll talk about that on Monday. But these are still power functions. So when n is less than 0, when your exponent, when your degree is less than 0, power functions like x to the negative 1 or x to the negative 2 are undefined at x equals 0. These functions will have discontinuities. These functions, domains, will not be negative infinity to infinity, okay? Because when you have a negative in your exponent, that can be written how? So that the exponent is positive. X to the power of 1. And we know from our work with the domains, what value can we not divide by?
0.
And remember, we always set the denominator not equal to 0. So at x equals 0, it makes the function undefined. That's why we'll have discontinuities. What type of discontinuity will we have? Is it a hole? Is it an asymptote? Or is it a jump?
Asymptote.
It's going to be an asymptote, okay? So when you have something like 2x to the negative 6, we're going to graph and analyze this one, 2x to the negative 6.
So which one would be a whole again?
Whole is if there's something cancels out and you have like a rational function. So a function divided by another function. So 2x to the negative 6 turns into 2 over x to the 6th. That is what that function essentially is, okay? Not going to use 2. That's going to give me something really crazy. So I'm going to use -1, 0, and +1. I might have to use a few others, but we'll see from here. If I plug in -1 for my x value, -1 to an even power is going to be what?
1.
+1. So at -1, I'm at +2. If I plug in 0, though, what happens? It's undefined. There is a vertical asymptote at 0. So I'm going to go ahead and put that in there. Remember, asymptotes are represented by dotted vertical lines. I'm also going to put in -1, +2. And when I plug in 1, what do I get? +2 as well. Doesn't give me much to work with. Okay? Doesn't give me much to work with. So let's use -2 and let's use +2. If I plug in -2 and I raise it to the 6th power, that's going to give me 2 over 64. 2 over 64 reduces down to be 1 over 32. That number is very close to what number? It's very close to 0. But is it 0? No. If I plug in +2, I get the exact same thing. Another number that's very close to 0, but not 0. I plug in -3 or -4 or +4 or -5, it's going to continue to give me a large 2 over a super large number. I don't know what 27 times 27 is, but it's going to give me another number that's very close to 0. All of those are going to give me a number that's very, very close to 0. But is there a number that will actually equal 0? No. On either side, it's going to be that way. These functions are going to continue to get really, really close to that x-axis, but they're never going to cross the x-axis or touch the x-axis. Same thing going if I were to plug in 1/2 or 1/3 or 1/4. These values are going to get really, really close to that y-axis, but never cross nor touch. This is what these functions look like. Is the domain all real numbers? No, it's from -infinity to what? 0. Is 0 included? No, remember there's a type of discontinuity there. But it does pick up after 0 until, so we connect that with the union. My range, what's the lowest this graph goes? Is it included? No, because remember, we can see that those values, when we plug in the -2 or the +2 or the -3 and the +3, is going to get really, really close to 0, but never actually equaling 0. What's the highest it goes? Very good. Do I have any intercepts? No.
No.
Because it doesn't cross the y-axis because there's a asymptote there, and it doesn't cross the x-axis either because my points will never get there. My end behavior, though. The limit as x approaches -infinity. So as x is approaching -infinity, what's happening to your y's?
They're decreased. Wait.
They are decreasing, but to what value?
0.
They're getting closer to 0. Think about it. Remember, when we're at -1, we're at 2. When we're at -2, we're at 132. When we're at 3, we're again getting a number that's closer and closer and closer to 0. So that is our end behavior as x is approaching -infinity. Look on the other side. As x gets bigger, what's happening to your y's? It also is getting closer to 0. So there's our end behavior. Okay, just look at the ends. What's happening? Is it continuous? What type of discontinuity is it? And where is it located? So if it's not continuous, you always state what type of discontinuity it is and where the discontinuity is occurring. It's increasing from what to what?
-infinity to 0.
-infinity to 0, and then it's decreasing from?
0 to infinity.
Very good. Remember, with increasing and decreasing, you read from left to right. In behavior, you start at the middle, go to the left, go to the right. That's how you analyze these types of power functions that have the negative exponent. We're gonna look at one more. And then we're gonna practice, because who knows how long we're in third period. So 2x to the -3 is the same thing as saying 2 over x to the 3rd power. Same thing as saying that. So when I make my quick table to take a look at my functions, I am going to use -2 this time. The reason why is because I'll be able to, it's only to the third power. It's not that big. What is negative 2 to the third power? So this becomes negative 2 over 8, which is the same thing as saying negative 1/4. When I plug in negative 1, what's negative 1 to the third power? So this becomes negative 2 over 1, which is just equal to negative 2. What happens when I plug in 0? Again, we have another asymptote at 0. When I plug in 1, I'll get a positive 2. And when I plug in 2, I'll get a positive 1/4. So when I plot these values, negative 2, negative 1/4, negative 1, negative 2, 1, 2, 2, 1/4. Well, I already know I want to get closer to the asymptotes on both of these sides, but what do you think is going to happen if I were to plug in positive 3? Or positive 4? Or positive 5? It's going to get closer to 0, but never reach 0. What do you think is going to happen if I were to plug in negative 3, negative 4, negative 5? Getting closer to 0, but never crossing 0. There are such things as horizontal asymptotes. We'll talk more in detail about them when we talk about rational functions in Unit 4. So I'm going to take a pause for a second. I want you guys to fill out all the information, analyze this function, and we'll see how you did. All right, Elizabeth, what you get for the domain? Around everything, yes, wonderful. Negative infinity to 0, union 0 to infinity, parentheses around everything because 0 is not included and infinity is not included. On the range side, let's go with Jemima. What did you get for the range?
0 and positive infinity with parentheses.
Mm-hmm. Okay, so that represents.
You can now release.
So 0 to infinity, that would give me this part right here. But what about that other pink part? Need another piece. I need another piece. Jada, what am I missing?
For the range,
Yes.
it would be 0 to negative. I mean, negative infinity to 0. I'm sorry.
Yes, I'll need the other piece too, and I'll need to connect them because as you can see, the lowest we go is negative infinity right here, and then we go all the way up to 0. We skip 0, and then we pick up the rest. Intercepts, Jackie. There are none. There are no intercepts. In behavior, online, the limit as x approaches negative infinity of my function is equal to what, Brandon? As x approaches negative infinity, as x is getting closer to negative infinity, what's happening to the y's?
It's getting closer to 0.
It is getting closer to 0. Thanks for the help out. Yes, it's getting closer to 0 because as we can see, as we get to -3 and -4 and -5, it's going to continue to get smaller and smaller and smaller. As x approaches positive infinity, though, on this side, going this way, Sky, what is what's our limit?
Also 0.
It is also 0. Very good, very good. Continuous. Allie, is it continuous? No, it's not. So that means I have a type of discontinuity. What is it? And where is it located? Make sure you put it as the actual x equals, actual equation of that asymptote.
Miss Anderson,
Yes.
I still don't understand the continuity.
Okay. So remember, continuity is basically points where the function's not continuous. If we're ever tracing over a graph and we have to pick up our pencil to continue to trace the rest of the graph, then that means we have some type of discontinuity. There are 3 types that we talked about when we did lesson 3-1. They were infinite, which were our vertical asymptotes, like what we've been dealing with. They were jumps, and those usually occur with what types of functions?
Piecewise.
Piecewise functions. That's when it would be defined on one value, but then it wouldn't be defined somewhere else. And then we had our removable discontinuities, which were also called what? They were also called holes. These occurred a lot of times with our rational functions, where we would have, it would be continuous, but then there would be like this open circle before the graph kept going. Okay? So these were the 3 different types. The reason why these power functions, the ones that have our variables in the denominator, the reason why they're infinite is because those are the values, or that's what occurs whenever we set the denominator equal to 0. Because we know we can't divide a number by 0. So any value that does make the denominator 0 means there's a vertical asymptote that occurs on those functions. So that's why for the last 2 that we've been doing, this one and the one before, we've had vertical asymptotes in each of them, because these are values that are undefined on our domain.
Thank you.
You're welcome.
Miss Anderson,
Yes.
would we also include the horizontal asymptote or no?
That's a great question, and we included in the range part. So if you notice for this one, like our range was everything but 0, because the graph is very close to 0 but never crosses or touches it. So horizontal asymptotes, they come into play for the range, but they're actually not points of discontinuity. Only vertical asymptotes are. Great question. Yes.
Will we ever have a horizontal asymptote without vertical asymptote?
Not in this class, but they do exist. So if anybody's thinking about continuing on to calculus, yes, you'll have them there. I don't think we give you any in this class, but they do exist. Online, increasing. Where? I'll take a volunteer.
Nowhere.
Nowhere. But it's decreasing where, Natalie? Start from left to right. So coming from the left. Okay. Help her out. Anna. So from -infinity to 0. So that's from all the way over here. The graph is decreasing with parentheses everywhere. And then it's also decreasing from 0 to infinity, because remember we have to pick up our pencil and then continue to trace over our graph, and it's still in a downward motion. So that's how you analyze. The main thing is if you can get the graph, you just got to be able to pull out that piece of information, those pieces of information. And behavior is something new, and we will continue to practice it when we get more and more into our different types of functions. This is still the functions unit.